Right? Nice recovery. Okay, let's get started. Okay, so just a few announcements. So this I've emailed out a couple of times. I'm holding my regular office hours. Oh, that doesn't work. I'm holding my regular office hours this week, which means yesterday from 10 to 11 to 12, and then Thursday 4 to 5 as usual. And then Monday and Tuesday of next week, I'll have 2 hours of office hours in the morning for folks who have last-minute questions. Okay, as usual, there's a forum for the final exam. I will post, I hope, some practice problems, although by this stage in the semester I've actually used up most of my practice problems on other stuff, so I'll send you out what I got. Okay, calculator, yes, I don't care what kind. You can bring, a graphing calculator, doesn't matter. You don't need a blue book. And then a little bit about the exam. So a few people have asked me, will it be more similar to the first midterm, which is a little bit on the hard side, or the second midterm, which is a little bit on the easy side? And I'm going to shoot for something a little bit closer to the first midterm. It will be not quite twice as long as a midterm. So 4 short answer questions instead of 2. And I don't know if that'll be choose 4 out of 5 or choose 4 out of 6 or something like that, or if it'll just be choose, answer all 4 of these. I'm not sure. And then 3 problem solving instead of 2. So it'll be twice as many short answer and 50% as many problem solving. And the problem solving questions will be the usual multi-part problems. They probably won't be particularly longer. They might go into a little bit more complicated stuff in some places. But I will try to maintain the usual distribution of sort of 20% of the point total being in sort of the harder category. And as I said before, approximately 2/3 of the material will be, 2/3 of the exam will be on material that we've learned since the second midterm. I do not guarantee that exactly 2/3 of the points will be, that's a rough estimate. This 20% will be precise. This 2/3 is a rough estimate. Okay. Any questions about the, yes? No, the short answer will be distributed across the whole semester, just like the problem solving. Now, yeah?
Should we be able to identify the readings from the whole semester as much as?
As much as possible. I wouldn't put too much energy into that. Yeah, maybe, if I, becoming familiar with the body of literature is not the point of this class. Okay? So if I want to make reference to some reading from the beginning of the semester, I might, do the usual author and date and then sort of remind you what it was about. And it won't be about tell me what, I'm not going to quiz you on that. So if I want you to think about a reading from earlier, I'll make it clear what reading I'm talking about. One thing I was going to say is that when I say 2/3 since midterm, there will certainly, within the problem solving, and probably within the shorter answer as well, there will be questions that require you to bring together material from different parts of the semester. So it won't be, say, for example, 2 problem solving questions from since the last midterm and 1 from before. It'll be problems that perhaps, for example, start out with some behavioral game theory thing and then start including some reference dependent thing or something like that. And so you can be fairly sure that I'll be mixing things together, especially in the problem solving. And we've seen some of that already, right? So I think we've seen some of that already, mixing together reference dependence with projection bias, that kind of thing. So that's highly likely. Any other questions about the exam? Okay, well, feel free to email me questions, and if you email me a question that seems like something everybody should know, I'll send it to everybody. Well, I'll answer it to everybody. All right, enough about that. So you've got this, and I'm going to leave it on the screen because otherwise, if I shut this off, it screws up the webcast. So I'm just going to leave that up there and maybe occasionally mark on it. Okay, so since the second midterm, we've seen 3 main topics, and on each topic, sort of one main model that you need to be conversant with, very familiar with, and able to work with. And this is not an exhaustive list. So as usual, what I'm going to do is I'm just, this handout should not be taken as an exhaustive list of everything you need to know. The exhaustive list of everything you need to know is in your notebook. It is all of the notes you've taken, all of the readings you've done, everything I put on a lecture slide, and every word that's come out of my mouth. So that's the exhaustive list. This is a good guide for where to focus your attention. And I won't go too much into particular math stuff because I just don't think that the time allows that. So we've talked about, the 3 topics we talked about are probability inference, social preferences, and game theory, behavioral game theory. Not all, but most of your thinking about probability inference should be built around a robust understanding of Bayes' rule. Okay, so what does Bayes' rule say? It says that the probability that a certain hypothesis is true, given that you've observed a certain signal, is equal to the probability that you would, it's the probability of that you would see the hypothesis and the signal at the same time, divided by the probability that you would see the signal at all without knowing whether the hypothesis was true. And that is usually equal to the probability of the hypothesis times the probability of seeing the signal conditional on the hypothesis being true, divided by sort of the sum over all possible hypotheses or all possible states of the world of the probability of H times the probability of I given H. Okay, so I'm doing notation on the fly, which is awkward. I'm sort of saying there's some set, right? Maybe I could say H element of, so some set of possible hypotheses, as HIV doesn't have HIV, right? High ability, medium ability, low ability, mutual fund manager. And basically what you're going to do is you're going to say, well, what's the probability that, for example, here's the universe of mutual fund, here's a universe in which I'm going to pick out 1/4 returns, right? And those returns are going to be from a high, medium, or low quality fund manager and are going to be either a positive or negative signal, right? And so, there's some subset of high, some subset of medium, and some subset of low quality managers, and within each of those, there's some probability that you would see a positive signal versus a negative signal, right? Something like that. And what you're doing is you're saying, let's take the event that when I randomly pull out 1/4 worth of returns, I get a positive signal from a high probability type, which is this area, and let's divide that by the sum of the probability. No, that one's mine. This one's yours. Right. So the numerator here is this area, right there, and the denominator is the sum of that area plus this area plus this area. And this is very similar to something that I drew during the semester. Okay. And you should understand this equality right? What is this fundamentally saying? What is a hypothesis? What is a signal? What is the okay, and then you should understand this equality, how to break these two things, numerator and denominator, down into the components that you can actually observe and calculate, and that you can think of as being areas on some kind of diagram like this. Okay? Hypothesis is always going to mean a hypothesis is always going to be this state of the world is true, or that state of the world is true, or something like that, right? And so we can also think about what in a situation where there's just 2 or 3 states of the world, right? It's just a yes/no to each of the 3 states. We could also think of a situation where there's sort of an infinite continuum of possible states of the world. How hard was that exam? It was anywhere between 0 and 100, and any real number between 0 and 100. And so rather than thinking about an infinite number of different hypotheses, its difficulty level was a 60, was a 61, so the 61.3 was E, was pi, right? Rather than thinking in those terms, we think in terms of what is the average difficulty level given what we know about the exam. So what's our prior belief about the average of the distribution of possible difficulty levels? And in that case, instead of having a hypothesis H here, you would have, instead of thinking in terms of the probability of H conditional on I, you would have a conditional expectation. What's the expectation of the difficulty level given what we know about your exam score, right? And you can think of Bayes' rule in very much the same terms, that the prior expectation of the difficulty level, right, the unconditional expectation of how difficult an exam was, is similar to the unconditional probability of a certain hypothesis being true, right? It's similar to a base rate. And you can think about the conditional expectation, the conditional expectation of seeing a certain score X given that the difficulty level, the average difficulty level was D, or sorry, that the difficulty level of the exam was D. You can think of that as being something similar to this, the probability of seeing a certain signal given the hypothesis is true, right? But don't worry, that part's not quite as important. I really want you to understand this hypothesis and signal way of framing Bayes' rule. And you should also try to understand how that is basically the same math or does the same work as Bayes' rule over a whole distribution of possible, a sort of continuous distribution of possible outcomes where we have to work with expectations instead of specific discrete hypotheses. Okay, now, question? Yes? What's usually the same? Oh, I guess what I meant was, in the discrete case where there's just a specific number of hypotheses and each one has a sorry? Yeah, exactly. If you were doing it in a case where you had some continuous thing like the difficulty level and you were doing conditional expectations instead of conditional probabilities, there are rules about how to compute conditional probability distributions using Bayes' rule. We haven't done that. I mentioned it when I was talking about the overconfidence, but we didn't actually do the math. But the math is ultimately very similar. And because we haven't done the math, I'm not going to require you to do anything like that on the exam. I might mention it, refer to it, ask you to comment on it. But in terms of math, it'll always be a discrete case where there's a certain number of possible hypotheses and a probability associated with each one. Okay? Now, within Bayes' rule, how do we actually get to behavioral economics? So let's understand the component parts of Bayes' rule first. There's a set of base rates. Okay? These are base rates. And then there's a set of conditional probabilities of the signal. Okay? Can everybody hear me? Is this thing working? Okay. So we're computing a conditional probability of the hypothesis given a signal. So the signal is observed, the hypothesis isn't. Then the component parts of Bayes' rule are, well, what was the probability that that hypothesis was going to be true before you saw any signal at all? And we always assume that you know that you know the underlying distribution of types or states of the world. That's the base rate, and it shows up in the numerator and denominator. Then there's the conditional probability that you would have seen the signal given that the hypothesis was true. In other words, what proportion of high fund managers actually does get a positive return each quarter. And we also assume in a rational model that you know that. And the only thing you don't know is whether or not this particular fund manager is high, low, or medium. Okay? But this also points us towards the two models that we've seen. We've looked at base rate neglect, and we've looked at the Freddie model, the belief in the law of small numbers. And you can think of them as basically affecting these two different components of Bayes' rule. The base rate neglect, which is a situation where we're trying to capture the psychologically realistic sort of observed fact, if you want, or stylized fact, that people tend to focus on new information, the signal, and ignore old information, the base rates, what they knew before about the distribution of possible types. And the way we model that is just by basically, we can think of it in terms of setting all of the base rates equal. We can also think of it as just simply eliminating the base rates from the model, because those are the same, mathematically the same thing. And then you can think about the model of belief in the law of small numbers, right? You had that model where if you have a series of independent signals, right, like draws from an urn. So there was I think I gave this as the Lost in Translation, the destroyer captain. That was on a problem set, right? It wasn't. Yeah, okay. So the destroyer captain hears a series of signals, a voice coming over a radio, distorted by static, right? Or you're trying to decide on a mutual fund. You have a series of signals, which are multiple quarters of stock returns for the mutual fund, mutual fund returns. Okay. And as long as we can assume that these signals are independent of one another, right? That the static on the radio is not always going to be more likely to be. It's not like whether or not there's static on the signal is independent from each signal. It's not like more likely that this boat will have static than that boat, or more likely that today there'll be static than tomorrow. But that every single signal that you hear from the small boat skipper is going to be either distorted or not distorted, completely independently of all other signals. Then we have a very standard probability theory that tells us how to compute the probability that you would have seen any given string of signals, right? Which is you just multiply the probability of each signal together, right? So the probability, if there's a 50% chance, say for example here, if there's a 50% chance that a medium quality fund manager would give you positive returns, then the probability that you would get positive returns two quarters in a row is just 50.5 times 0.5. And then the belief in the law of small numbers gives us a way of capturing the idea that people think that those probabilities aren't actually independent, and that the more you've seen positive, the more likely it is that the next draw will be negative, right? That people think that sort of like a coin that gets tossed, that somehow coming up heads requires some effort on the part of the coin, and it will get tired, and after a while it will just sort of, oh, come on, there's no way this coin can put out one more heads. It's got to bail out towards tails, because by this time its heads muscle is just getting fatigued, right? And so we model that with, instead of draws from an urn with replacement, we have draws from an urn without replacement, and you need to understand what that means and what that does to probabilities, and then you just do exactly the same thing. If the probability of pulling out, if the urn has 2 balls in it, let's say the urn has 4 balls in it, the probability of pulling out a positive return in the first quarter is 1 in 4. Now there's 3 balls left in the urn, only one of them is positive. The probability of pulling out a second positive is now 1 in 3. So you just need to understand how to do that, and what you're doing there when you apply that Freddy rule of without replacement instead of with replacement, is you're figuring out Freddy's false belief about the conditional probability of seeing a signal. Right? So you're computing this part of the model, the part with the conditional probabilities of signals. And the one thing that some people got tripped up on with that was the difference between an individual signal and a sort of combined series of signals. So for example, we can use the term signal to refer to a single quarter's worth of returns, or we could use the term signal to mean observing 2 quarters in a row of positive returns. And you just need to be very careful when you're solving a problem to understand exactly what I mean by signal in any particular case. If we're dealing with Freddy, then I'm going to be talking about a series of signals, because that's what Freddy gets wrong. Right? Does that make sense? Okay. Okay, so I'm jumping around a little bit here. Where do I want pen. How do I get the pen? There we go. No? That's highlight. All right, well. Then we just won't write on it. Fine. Okay, so I talked about multiple signals versus a single signal, 2 different quasi-Bayesian models. We talked quite a lot about the implications of the law of belief in the law of small numbers. And, there were a series of implications, all of which came under the heading more or less of overinference. So you should understand how belief in the law of small numbers leads to overinference, right? So in other words, winding up placing too much weight on a signal, or inferring too much from a signal about the underlying distribution of states of the world. And you should know how to think a little bit about the economic implications of that. Then we talked about different explanations for people having incorrect inference, probability inference. Right? So this is all, to some extent, under the heading of rational versus irrational expectations. The idea behind the assumption of rational expectations is that people know not what's going to happen in the future, but that they correctly understand the probability distribution of possible things that might happen in the future. Okay? And that applies to an extremely broad range of different concepts. Right? So we include in that people know correctly the distribution of possible states of the world when they're inferring probabilities, but we also refer to that as they don't know exactly whether they're going to become addicted after a month of going to the gym, but they know the they don't know the probability that they'll form a gym habit after a month of going to the gym, but they know the probability that they will. Or they know the distribution of probabilities of how likely it is that they'll form a strong versus a weak habit. Okay? And that shows up over and over and over again. But included in the assumption of rational expectations, right, is things like, we've seen over and over again that there are important decisions where you've got to be able to infer the probability of something that you don't actually know. Okay? We don't actually know. We know the base rates. We know how likely it is that someone's high, medium, or low type. We know the conditional probability of seeing a positive signal conditional type. We don't actually know from prior experience what is the probability of a high type given a positive signal. We have to infer it, and we're supposed to do some math. And so we could get that wrong. Right? Rational expectations requires that individuals not only know these base rates and these conditional probabilities, but that they do the inference right to compute the new probability that we want them to understand in our model. And so that requires not only that they have a correct understanding of distributions of probabilities, but that they also know how to apply Bayes' rule. And so we get into the overlap between rational expectations and unbounded rationality, unbounded sort of computational ability. And we can get into a situation where, hey, people actually do know they have rational expectations about the base rates. They have rational expectations about the conditional probability of individual signals. But for one reason or another, they fail to apply Bayes' rule in a rational way. Right? So they have some failure of the assumption of unbounded rationality that results in them having an incorrect belief about the probability of a certain state of the world. So they started out with rational expectations about a bunch of stuff they already knew. They didn't have biased beliefs about how likely it is that someone's a high ability, a biased belief about the distribution of high ability types. But after we required them in our model, for some reason, to make a decision based on an inference, because they do the math wrong, or because they act as if they're doing the math wrong, they wind up with a biased belief about some conditional probability, right? Some hypothesis being true. And so bounded rationality can lead to irrational expectations. And we'll see that again. Okay. Okay, so I just talked about that. Now I'm going to back up and talk about this. Okay, so we talked about different reasons why people might wind up with incorrect beliefs about probabilities, incorrect inference. And I just sort of said, well, it could come from people actually not knowing probabilities correctly. It could come from bounded rationality because they don't know how to apply Bayes' rule. And then, but then we could think about a few other sort of more deeper reasons for why this might be the case. We talked about the sort of Tversky and Kahneman heuristics and biases framework, which is sort of the story about bounded rationality, right? It sort of says inferring probabilities or making decisions is cognitively burdensome, difficult, and so to save cognitive effort, or maybe just because you don't know how to do the math, people have shortcuts, heuristics, okay? And these heuristics, in a lot of situations, get us a fairly good answer, but not a perfect answer. But then in certain situations, they actually give us systematically and substantially wrong answers, which become biases. So you have a heuristic, it doesn't automatically lead to a bias, but in certain situations, it may actually lead to a systematic bias. So for example, if the heuristic is, just ignore the base rate, because in a lot of important situations, the base rate doesn't matter, okay, and I get pretty close answers by ignoring the base rate, then there will be certain situations in which, in fact, ignoring the base rate is a bad heuristic, and you wind up with a big bias, okay? So you want to understand what the heuristics and biases framework means, and that's well explained in the assigned paper. Then we talk a little bit about the idea that maybe, in some cases, this isn't a story of bounded versus unbounded rationality or heuristics and biases, but that we're actually hardwired to make certain mistakes in order to protect us from sort of prehistoric dangers, right? And we talk about the situations